Can you settle an argument with math? Bob and Linda are planning their 16-day vacation. Linda wants to spend it at the beach. However, Bob would rather go camping in the mountains. Bob and Linda own and run a family burger shop with their kids, and this is their first vacation in years. After some arguing back and forth, Linda and Bob ask the kids if they will help them decide the fairest way to settle the argument. You see, if they can't come to an agreement, the alternative is they stay home and work in the restaurant. This is not the outcome Bob wants. The stay-home option, otherwise known as the do-nothing option, is known as the status quo. Their oldest daughter Tina decides that utility theory is their best approach. So the options are beach, mountain, or status quo, stay home. Tina asks her parents to rank the choices from greatest to least, and Bob realizes that he and Linda have opposite preferences. So then Tina suggests that each of them assign a numerical value or utility to their choices, giving them a number ranking between 1 and 10, where 10 is best. Let's look at how Bob preferred his choices. So here, Bob gave going to the mountains a 10, where staying home or status quo a 7, and going to the beach a 6. Measuring the differences in his values, we see that Bob likes going to the mountains over staying home 3 times more than staying home over going to the beach. Now, Bob would just be happy staying home, so he would let a lottery decide between going to the beach or M just as much as he would like staying home. So choosing probabilities that balance his preferences would be one way to do this fairly. So if we let the beach choice be 3 times as likely as going to the mountains, that would help balance it out for his wanting to go to the mountains 3 times as much. Now, normalizing the rankings of each person means that we can add or subtract values to each of their particular values so that status quo has a value of 0. That's called normalizing. And now, by taking their values and creating coordinates, we could create this thing called a payoff polygon, and that would help us decide the lottery. So now, using the utilities, what would the utility of a lottery such as that look like? We create a utility equation, which is really a linear combination of the utilities and their probabilities. So for the proposed 3/4 and 1/4 beach mountain option here, the utility equation gives us values for both Bob and Linda. And it's a point on the polygon. It's a 0.05, meaning that this fair lottery would give Bob a value of 0 and Linda a value of 5 because her preferences were relatively stronger. But how good is this type of an outcome? Is there a more optimal solution? In 1950, John Nash, mathematician and Nobel Prize winner, found a way to satisfy a set of good and fairness conditions by maximizing a product using the northeast boundary of a polygon. So the equation of that northeast boundary is put together with a product xy, where y is the boundary, and we get a product equation which can be maximized through calculus. Now, using the first derivative, we find a critical point on the boundary, or the x value that gives us the critical point, and that is x equals 5/4 here. By utilizing that and looking at the product is maximized at this critical point. So then plugging that critical point into the boundary equation, we find the y value of 5/2, giving us the Nash Equilibrium point, 5/4, 5/2, which is a point that corresponds to a lottery between going to the beach and the mountains. And with these values, we can then use the lottery utility equation to calculate the probabilities that each of those things should be done at. So, the Nash arbitration solution gives us utility values, and we take those utility values, apply it to the utility equation. So here Bob has a lottery utility of 5/4. We're going to use that to find the probability P, and thus 1 minus P. And here we find P to be 7/16 and 1 minus P to be 9/16. The interpretation of this is that 7/16 of the time we would go to the beach, and 9/16 of the time we would go to the mountains and go camping. We could say that if they're going to have a 16-day vacation, you would go 7 days to the beach and 9 days to the mountains. So there you have it. We've settled the argument with math. The Nash arbitration scheme has given us a way of deciding how to happily enjoy a 16-day vacation. And this solution can be applied to more choices.
Adam Smith said, best result comes from everyone in the group doing what's best for himself, right? That's what he said, that's right? Incomplete. Okay? Because the best result would come from everyone in the group doing what's best for himself and the group.
Nash, this is some way.
And now it's time for a more advanced problem. Bob and Linda, the management here, and their kids, Tina, Jean, and Louise, their labor, are deciding what to do for the school year. The new school year has come up. The kids are expected to work after school Tuesdays, Thursdays, and Fridays, Saturday and Sunday, with a 15-minute break each of their shift. So now, the kids, as the labor, have some new set of demands for the new school year. The kids are negotiating the following. They would like a $1 per hour raise to their allowance/salary, one of the weekend days off, and management here is concerned about the kids abusing their 15-minute break, stretching it to 30 minutes, so they want to eliminate that break, as well as hire a cleaning service which would fire one of the kids. Status quo would mean they don't change anything from last year. Now with this, there are 16 possible outcome combinations to consider where the single outcomes are valued independently, making the utilities additive. That simply means that any combination of choices could be just take each utility and add them together. So now, suppose the following normalized utilities where status quo is set to 0. We see for management and labor the set of utility values that they've chosen. The labor wants to raise more than their extra day off and dislikes eliminating a worker more than eliminating their 15-minute break. Also note that certain outcomes like a combination of cleaning service, eliminating the 15-minute break, and the raise is no different than staying home, so that might not be the optimal choice to choose here. So now your task. It's your turn to decide. What you'll need to do here is take the information, create a payoff polygon, find the Nash arbitration point n that maximizes the product, and interpret the results. Good luck! And stay tuned for the results in our next video. Hey, thanks for watching. Please hit the like, subscribe, and notification bell for more videos.